Lesson 887, Pictures to Prove It, Exploring Squares and Right Triangles. In this lesson, you'll understand one proof of the Pythagorean theorem. You'll also calculate unknown side lengths of a right triangle by using the Pythagorean theorem. All right, we're on page 190 in your notebook. And there's a couple of learning targets today. One of them is to explain why the Pythagorean theorem is true for every right triangle. Explain why the Pythagorean theorem and from here on out I'm just going to abbreviate that PT is true for every right triangle. And secondly, we'll use the Pythagorean theorem, I'm going to say PT, to find unknown side lengths in right triangles. Okay, so this is building on what we've talked about for the last couple of lessons. We've already seen that a squared plus b squared equals c squared. That's true for many right triangles that have legs, the short sides of the triangles. We'll call them A and B. And today we're going to show that this is always true using what's called a proof. That's how mathematicians verify that what they're saying can be used to build to other things. Proofs help us know when a relationship will always be true. So in the lesson today, you had two figures that looked like this, and you found that the areas represented on one side were actually the same as what was on the other side. Let's take a look. I'm trying to find my pink highlighter. Here we go. So we're going to take a look at the area of the pieces in these figures. For example, this pink piece is a square with sides of A and A. So the area of this piece is A squared. This pink part is B times B. So the area of this is going to be B squared. And then we have these other pieces that aren't shaded pink. These aren't quite as easy to calculate, but we'll write down their areas in just a moment. It's just the length times the width of that rectangle, A times B, or AB, for both of them. And we can find the area of this whole figure. We can find the area of this whole figure. And what you saw in the activity today was that we could rearrange all these blue triangles to be the same as the two blue rectangles on the other side. We could kind of put those triangles together. And if all of those blue shapes were equal, then the pink shapes had to be equal as well. Okay. So this isn't exactly the same as the proof that we saw today, but it's another way to prove that a squared plus b squared equals c squared. So Habib wrote the following proof of the Pythagorean theorem based on these diagrams, figure G and figure H. Let's start with figure G here. He's just adding up all of these pieces. To represent this whole square. Well, that whole square is made up of a squared, this pink square down here, b squared, and then these two rectangles that are each a times b. That one's a times b, this one's a times b. So that's figure G. And it's the same size as figure H. So we've got that square in the middle, c times c is c squared. And then we have 4 triangles. the area of a triangle is 1/2 times the base times the height, or 1/2 times A times B. All right. So he set up this equation. He made the area of figure G equal to the area of figure H. And now we can just treat this like a regular equation. I'm going to simplify what I see here on the left. I see that I can, since this is AB and another AB, I really have two AB. And I have the A squared plus the B squared. So we just combined those two squares, or two rectangles that had areas of AB. On the other figure, we had C squared. And if we were to simplify this, our four triangles, 4 times 1/2 is just 2 times A times B. So it looks like I have 2AB on both sides of this equation. And we talked about balancing equations earlier this year. I could just subtract this from both sides and keep my equation balanced. And when I subtract it from both sides, all that will be left on the left side would be A squared plus B squared, because 2AB minus 2AB cancels out. And all that's left on the right side is C squared, because 2AB minus 2AB cancels out. Now, I don't need for you to be able to do all of this for yourself. I just need for you to be able to understand how this is true. So, just to recap, what he did was he found the area of each figure. What he did to prove it by adding up all the parts. He wrote the areas equal to each other. Figure G's area was equal to figure H's area. That's what he did right here. There's all of figure G, there's all of figure H, set them equal to each other. And then he was able to simplify and subtract 2AB from both sides. Oops, from each side. And that left us with A squared plus B squared equals C squared. So that's one way to prove that this fact is true. So that's the first thing we wanted to be able to do, is just explain why the Pythagorean theorem is true for every right triangle. It wouldn't matter what the values of A and B were. It would work every time the same way with this proof. The second goal we have is to use the Pythagorean theorem to find unknown side lengths in right triangles. So let's do that to find the value of x in this figure. Well, the trick to using the Pythagorean theorem is finding right triangles that are useful to us. Well, we're finding the value of x. So x is right here. And I'm going to see, is that segment part of any right triangle? And the answer is yes. I know that this side and this side make a right angle. So these two yellow legs in this blue hypotenuse actually make a right triangle. I'm going to mark the right angle here just so we're seeing it. So this is the hypotenuse. So let's use the Pythagorean theorem. Here it is. First thing we're going to do is just substitute in any values we can for A, B, and C. Well, we know the hypotenuse is what C is supposed to be. That's what we're looking for. I'm just going to put X here. As long as we get the hypotenuse right, the other two sides we can call whichever one A or B. Doesn't matter which one's A and which one's B. So I'm going to call this one A. And the formula says I need to square that. I'm going to call this one B in my triangle. So B is 7, and I have to square that. And let me simplify this now. I'm going to follow the order of operations, doing exponents first. 1 squared is 1. 7 squared is 49. So 1 plus 49 is 50. Now remember, I wasn't asked for X. I was asked for X. I'm sorry, I wasn't asked for X squared. I was asked for X. I know what X squared is. So if I want to know what just X is, I have to do the inverse of squaring. Well, the inverse of squaring something is taking its square root. We said before that squaring and square rooting, since they're inverse operations, they really cancel each other out. So if I take some value like X and I square it and then take the square root, I'm right back where I started. So I've got X when I took the square root of X squared. And the square root of 50 is what I'm left with. So I found the value of X. So to use this formula, I'd like to write it down first. Make sure that you get the hypotenuse right. And then just fill in all the other values and simplify. All right, so in summary, let's take a look at how we can see this equation in this figure and explain how this relates to the Pythagorean theorem. Well, 5 squared plus 12 squared equals 13 squared. Well, I see 5 squared right here. I see 12 squared. Well, I know that this side is 12, this side is 12. 12 times 12 must be 12 squared, or 144. And since I know that the shaded areas in this figure are the same as the shaded area in this figure, I'm going to have to do a little simplifying here. Let's see, 5 squared is 25. 12 squared is 144. I know that this has to be 25 plus 144, which is 169, which is actually 13 times 13. So since the area shaded on the left figure is the same as the area shaded in the right figure, I can see that this is going to be the case. So the shaded area here on the left is the same as the shaded area on the right.